Okay, here's a good one for you. You're going to like it. Diffraction and interference, some of light's most interesting properties. Okay, we have a diffraction grating, it says. We can still draw a picture of this. This is the diffraction grating. Top view. So light is coming into this diffraction grating, and the way the diffraction grating is set up, it has a whole bunch of lines very close together. So the light comes in this side, and what happens is that the light undergoes diffraction and interference and shows up over here on a screen in a really odd way. It says that this is a 633 nanometer wavelength light, so that's red. So we'll make this light red. It's coming in. Red light. And what it does when it goes through this diffraction grating is it produces a pattern onto the screen. And the pattern is really interesting. It has a bright spot in the center, and a dim spot, and then a bright spot, and then more dim spots and bright spots like this, and so forth along the way. Bright and dim spots. So that's what diffraction and interference does. That's what it's all about. So then we know a few things. That is, we know that the distance between the diffraction grating and the screen is 3 meters. And we also know that the bright spots are 4 centimeters apart. So this is 4 centimeters. Okay. So do we have a physics principle for this? Yeah, we do. It's kind of a good one, actually. It's one that says sine lambda equals, sine theta is equal to m lambda over d. So what's theta? Well, from the diagram, you can see it, as it turns out, pretty easily. Because if you make the triangle defined by the diffraction grating, the spot where the central maximum is on the screen, and the spot where the bright spot is, first bright spot to one side, then here's your angle theta. So let's see, what are we after? Here's what it says. It says how far apart are the slits. So what we're trying to find then is d, the distance between the slits. We can get, or we know lambda, that was told 633 nanometers. And so how can we get theta? Well, we have side opposite theta, then we have this length, which is the side adjacent, so we can say tan theta is equal to x, the 4 centimeters, divided by L, so we can find theta from that. Theta turns out to be 0.764 degrees. So, small angle, you bet. So then, if we solve this for d, we find that d is equal to m lambda over sine theta. Now what's m? That's an integer that defines which of the bright spots this is. And this is the first bright spot off to the side of the center, so m is 1. So now we can put in the lambda and the sine theta and solve for d, and it turns out that d is 4.75 times 10 to the minus 5 meters. This one's a little tougher because it's hard for you to make a good estimate of whether that's an accurate number or not, because it's very small. And of course, the way diffraction gratings work, the ones that are really good are ones that are cut very close to each other. So this is a good one. We'll take that.